Welcome back. This is class 3, and we continue our journey in regression analyses. So once again, I have basically uploaded the files of Professor Sang, which includes the lecture file, the RMD file, a PNG file named confounder, and a PNG file called correlation slope. These three files together need to be copied in one folder. And as in previous lecture, I've outlined, please open a folder on your desktop that basically routes BIOS620 to class 3 and to a folder labeled lecture. I think it makes sense that we all kind of uniformly label these files because it makes it easier for explanatory purposes. Okay, so I've initiated, when we started talking, I've initiated the process to essentially knit the markdown file together. I have copied PNG files, both PNG files in the same folder. The markdown does not refer to any folder structures, so as long as they're in the same folder, it's fine. It will then create for you a PDF file, which you see here. And this is going to be the PDF file we will be talking about today. All right, so I'm recording this a little bit in advance because I'm traveling for work purposes, but you will see this class on Monday the 13th. All right, applied biostatistics 1, we are at class 3. Good. So first, I want to talk briefly about some discussion points that were brought up in previous classes, which Professor Sang has outlined based on what had been discussed during the first two classes. And I intentionally left these slides in because I think these are very fundamental kind of conversation that need to be had in the context of what we have been discussing. And these discussions that had occurred during previous classes may be representative of questions that you may be having at this point. So for that very reason, I left the slides in and I thought we're briefly going to talk about this. Good. So firstly, we're going to talk about the difference between standard deviation and standard error. So you likely will recall this distinction, but I will briefly show some slides on the central limit theorem and walk us through that distinction between both markers of variability, because they essentially imply and reflect something different. Then we will be talking about the differences in normalization, standardization, and centralization. So these also, it's not entirely surprising that these conversation topics came up because we are normalizing data. By normalizing data for the lab in class 2, we have normalized data, log normalized data, log transformed data. This is a form of normalization, we basically, and we'll talk about it, how you get data back on a normal level, where standardization is what we did, for example, for the regression example, right? Where I briefly showed you, okay, so we have a set score, we have a set score of X, and we come from this set X to set Y hat by multiplying it with the R, with the correlation coefficient that essentially gives you a strength of this association and a certain reflection of the slope. And then we come to a set Y hat, and from a set Y hat, we get, knowing the mean of a Y, we get on the level of a Y hat. And this is our prediction, this is our slope. This is then this transformation of an actual value of any variable in reference to mean and standard deviation. This is what's being referred to as standardization. This essentially gives you a handle on localizing every point along an entire spectrum of points, across an entire magnitude of points, using two population parameters that you are meant in set statistics to have at your disposition. And this just allows you to characterize and to estimate from your population approximately what proportion, or what fraction of your population will be within a certain magnitude of ranges quantified as per standard deviations. So you may remember from introductory statistics, I hope you remember from introductory statistics that this is how this is done. And you essentially with a set distribution, you can actually quantify, okay, so I have a blood pressure of 120. So I'm talking too much about it. I wanted to show you the slides actually. But you have a blood pressure of 120, you have a standard deviation of 10, and you essentially capture going 10 higher, well, from 130 to 110. So 110 to 130 will capture for you essentially 68% of your population. And this is powerful knowledge to have when it comes to population statistics, right? Centralization is essentially what we talked about last time with the blood glucose example. And lastly, and I'm getting away from this introductory outline slide. So we talked about the association between person correlation and the slope from a simple linear regression. So it's two different things, but they are to some extent connected. So there's some interdependency which allows you to estimate one from another, but they are succinctly different things. Good. Okay, standard deviation and standard error. So in a simple regression model, like this here, right? So we have a yi, which is our response variable. We have the beta 0, which is our intercept. We have the beta 1, which is the slope. We have the xi, which is the individual entry on the x-axis. And we have the residual error, where the residual error is normally distributed around the mean of 0 with a variance of certain magnitude. So we have I equals 1 to I equals n, which is the sample size. So now we have the variance is the variance of the error term EI. So this EI is the residual error around that model. And we have looked at this. Can you remember this was that graph we had of empty cars from last labs? We had miles per gallon as a function of weight, and we had our individual entries, and then we had app lines fitting a line through, and then we had this difference between the predicted y and the actual y. And that difference essentially is a residual. So this residual is distributed in certain shape or form, and this is meant to be normally distributed, at least approximately normally distributed. We also, for our simulated model or for our car model, we saw a little bit of a difference between the median and 0. So if the median is smaller, then it's lower than the airplane. If it's higher, it's larger than the airplane, because it's yi minus y hat. So now this distributes with a variance, with a certain variance, and I just realized I'm not sharing my screen yet, which is terrible. So please, sorry for that. That's actually bad. Okay, so now you have me. Trying to outline, trying to show graphs. Okay. So these are differences in ST and SI, normalization, standardization, centralization, person correlation. So these are the things, these are the advantages. So the examples I gave, you have this in your slides. So it's not, it wasn't anything I really showed. I was just talking about it. Okay, so this is the regression model I was referring to, yi, beta 0, beta 1, slope, and xi and ei. Ei normally distributed around the mean of 0 with a variance resembling the variance of each individual entry in reference to the corresponding y hat. So this pair between yi and y hat will give you the entire pool of residuals, and these residuals are distributed in certain shape or form. And this is normal distributed around the mean of 0. And if the median is differing from 0, then you have a little bit of skewed residual distribution, which in many cases is just something we accept. in our context, we can accept it. So then we have variance. Variance is the error term EI. So the standard deviation is essentially the standard deviation of the error term EI, and this is the standard deviation of the residuals. So sigma is an unknown parameter, obviously, because you can only estimate it from the data, and we will talk about this in the former in the next classes. And yeah. So then I also recalled that in last class I remained owing you what IID stands for. So this class now here finally features it. So again, this is IID, and this is one of the conditio sine qua non. So this is actually this is a precondition that you need to have fully fulfilled to essentially be able to do regression analysis. So IID stands for independent and identically distributed random variables. So every data point in this random variable needs to be an independent measure. And the distribution needs to be identical, the entire range of magnitude. This is central to regression analysis. The standard error refers to the precision of estimate. For example, the standard error of Peter's hat, 0. So this would be, this can be used to calculate 95% confidence interval in the p-value. It's very complicated to calculate in regression and will be covered later on. So it's actually, so there is an association that is to some extent a little bit more complicated than what you essentially seeing with the standard deviation of the residuals alone. So it is something that needs to be discussed in more detail. So normalization is referring to rescaling. Rescaling of a continuous response variable. This can be done with a logarithm, a square root. And you're doing that with the intention to meet the normality assumption. So this will not always be the case. So as you remember, we have 4 random variables that act as a response variable, dependent variable. We have to have a normal distribution assumption, not for the covariates. However, this will be discussed in more detail. And what we also, in my world, for example, in the world of physiology and the world of medicine, a lot of what normalization there refers to is normalization to other body-related parameters. Classic example from my world, glomerular filtration rate, which is a marker of kidney function, which is known to be standardized to the average body surface area of 1.73 square meters. So, so you essentially get a value. You get a value of a glomerular filtration rate. Usually, you don't get a GFR. Usually, you get what is called a creatinine clearance or a urea clearance, which relates to the glomerular filtration rate, quantified with something like inulin. But this is getting too technical at this point. But you get a clearance rate. You get a clearance of how much your kidney actually can clear over a certain period of time. So this is usually quantified in milliliter per minute. And you're taking now this estimate as per milliliter per minute, and you're standardizing it to the body surface area of that patient you're having in front of you. And that body surface area, again, is being calculated using an approximation formula, which is notably from 1918 by scientists Dubois, and they have quantified it in 1918. and you're taking the population average of 1.73 square meters. Problem with that is the 1.73. So you're using this estimation of the body surface area of your patient, and then you're standardizing and normalizing it down. So you first normalizing it to 1.73. So you get an actual body surface area and you're normalizing it down to 1.73, that it complies with this 1.73. By that, you're normalizing it to one standardized parameter. So, okay, it couldn't be any more complicated, I understand that, but essentially what you're doing is you're normalizing your result, and you're normalizing it to body surface area, and then you use it for standardization. Another example is that, for example, you would standardize protein catabolic rate. So protein intake can, in my dialysis world, be normalized to body weight. So the problem with protein catabolic rate is and protein metabolism, this will reflect to some extent, will be associated to the individual per se. So somebody who has higher BMI, who's just used to eat more, will eat more and will have a higher protein metabolism as compared to, I don't know, a lovely old lady in her 80s. So it's just, it's a natural phenomenon, right? So for that very reason, you standardize it, or you normalize it to body weight. And by that, you get an estimate of a weight specific, body weight specific, standardized, normalized protein metabolism. So this is normalization. Standardization is what we have been doing in last class with the correlation coefficient and the association between the mean and the standard deviation. And I talked about it already earlier. So this is essentially, you are standardizing a normal distribution with a 0 mean and 1 unit of standard deviation. So yeah, you can quickly find p-values in set statistics. So in pre-computer time means like this was before computers were done, this was how hypothesis testing was done. And yeah, you still can do it. And I think many of you may have learned it in introductory statistics at one point. I'm teaching to my undergrads, for example. So that's you kind of you still should understand the basics of it. And I think you've learned it in the earlier introductory statistics course. Those of you that are interested, I'm happy to discuss it in the discussion board, or direct you to literature or information outside in the top. Lastly, centralization is referring to the shifting of a covariate by subtracting its mean from the original value to facilitate interpretation. So what you're doing by that, essentially, you're shifting the intercept. So you remember we had this example in last class with centralization of the glucose, which again resulted in a glucose value that was too high. But besides that, we had a shift that shifted this reference value. So it was not the intercept anymore. It was now suddenly something that was higher and that was closer to the mean. So essentially, or it was essentially the mean. So what you have essentially is you retain the same slope, but you're shifting your reference intercept. And that just makes more sense because essentially you're getting now the y at that point where x equals the mean of x. It's making more sense in terms of interpretation. If you look at the serum glucose of 0, that is just a serum glucose that is not acceptable with life. So from that end, it's facilitating interpretation. Good. So these are these three terms, and I think this is quite important. And the last conversation piece that we have here to have is the correlation coefficient and the slope. So we have essentially we have a range where the correlation coefficient is between -1 and +1, whereas beta 1 can be arbitrary. It refers to last class for the interpretation of the regression coefficient, beta 1 on the simple linear regression. And the difference here is really that you have standardized regression coefficient. And by this standardization, you essentially, you can leverage this association between slope and correlation, but in its own right, these two are separate entities and to be treated separately. Good. All right, so this was this recap. I encourage you to also go back to last class to look at the calculation of slope and intercept, but they are entirely different entities. And this needs to be understood for moving forward. Okay, class 3. What are we talking about today? So we talk about multivariate linear regression. We will be talking about the rationale to include more than one covariate. We'll talk about confounding and confounder, really in very broad terms, because it's like you will talk about this in much more detail than in epidemiology classes. Then we will talk about the loss when not conducting RCTs, which refers to the nature of observational studies. Also more of an epidemiology topic, but we're briefly going to touch on this. Then we're going to talk about fitting models that address confounding in R. We talk about the interpretation. We will again talk briefly about R's output, although we did that in the last class, and look into the distinction between R square and adjusted R square. Lab 3 will be talking about the simulation and detection of unobserved confounders, and we will code a for loop, which is an iterative loop that essentially is one of the real essentials. And you will see why, a very useful feature. Okay, a regression with 2 or more independent variables. Why do we need to consider this? For obvious reasons, right? So you have, you want to control for confounders, you want to control for effect modifiers, you want to increase your accuracy overall, and you want to get a handle on special data. So we will be talking about all of these, specifically, just let's briefly talk about segmented regression is essentially where you have different slopes and different associations with different piecewise segments within the range of your data. This is something which will not be subject of this course. You will learn more about this when you think about spline functions, for example. They kind of are being preceded by segmented regression in a way. But yeah, this is ultimately at this point. Increase the prediction accuracy because you're kind of explaining away part of this unexplained variability, which is also then affecting the accuracy, and essentially also affecting your R square, which is essentially is the resulting error over the total error. So essentially you will kind of be able to minimize the unknown error, the unaccounted error. All right. So confounding. What is confounding? So we are aiming still to investigate the relationship between serum glucose and systolic blood pressure. So we know that there's a physiologic reason associating serum glucose with serum systolic blood pressure. So we know there's an association. So we know that happens. And I mentioned last time already, so this will change with age, right? So in a young individual, glucose may have an increasing effect on systolic blood pressure. In an older individual where you have different reasons coming into play that could also affect blood pressure, like for example, stiffening of the vessels or atherosclerotic changes or changes in the cardiovascular system, coronary atherosclerosis that essentially compromises cardiac function and consequently systolic blood pressure. all of these will essentially be affected by aging. So now this goes in one direction, the other direction. So if you have a stiffening of the vessels, the blood pressure goes up. If you have decreasing cardiac function, blood pressure goes down. So basically both of these directions, so it's getting a little tricky. For this very reason, you want to adjust for age, or you want to account for age in your model. So empirically and biologically, we found that older people tend to have higher serum glucose, which is the next problem, right? So age essentially will also affect your exposure. So we have on the pathway from exposure to outcome, exposure being glucose, outcome being blood pressure, we have a parameter or variable that essentially affects both outcome, blood pressure, as well as glucose. So that is a classical confounder. So when this essentially happens, that association is confounded by age. So if we have only a group of individuals of the same age, this cannot be a problem, right? So if we have a group of only 20-year-olds, this would not be a problem. So, but we have a wide range of age. But the question is now, how do we get a more reliable estimate of such a relationship? The answer is essentially by accounting for age. So we have, okay, the definition of a confounder, X with a pathway to Y, so exposure to outcome, is confounded by C that essentially confounds both exposure and outcome. So example one, X equals glucose, Y is systolic blood pressure, C is age. The same may hold true with physical activity, Y is heart disease, and C is age. A third example could be CUNY's MPH admission rate between 2019 and 2020. So what is the outcome? The Y is the admission rate, right? What is the study variable? That would be year. And now what could be confounders? I would argue one of the confounders could be a certain pandemic that has happened, but I think that's what he was referring to. So, so there are really, so this is also referring already to a period effect, right? So also in period, you have changes over that are affecting things on a more fundamental level. And you will talk about this in, I think should be EPI 2, where you will be talking about the so-called APC, age period cohort effect. So you have, that is this interplay between an aging cohort, then you have a cohort with certain demographics, certain clinical characteristics, and you have the period where basically when you observe, particularly you observe it over 20 years, you have a period effect in various parameters. It could be documentation, could be practice patterns, could be screening patterns, could be technical capabilities. So there are differences. And so when you look at an MPH admission rate, I would argue that when you have a pandemic going on, nobody can travel, nobody can actually go in person to attend courses, and the admission rates will drop. And I think this is what it's meant to. Good. Address the confounding issue. At study design stage, we could conduct a randomized controlled trial. So now you have in a randomized controlled trial, you have at the beginning of a trial, you basically, and you will learn this in trial design, you have the so-called exchangeability given, which means that you essentially have two groups, you have two arms. Simplest example, you have an RCT with two arms, and you draw one person out, you draw one person of the other arm out, and then you drop them in the opposite arm. That basically doesn't change the distribution. That means they are balanced between both arms, And small differences will not, if you randomly pick from one and you exchange it randomly with another, that doesn't change the distribution of either arm and neither of the overall study population. So essentially, you are by that, you know, that the arms are balanced in terms of demographics, clinical characteristics, everything that could be relevant in the context of confounding. Because if you have a disbalance of one demographic, for example, age, let's use age as a good example. We have an older age in one group versus the other age, and you conducting a randomized controlled trial, which at this point wouldn't be randomized, would be more of a cohort study, and the cohort marches in one direction, and you're basically observing them over 2 years, and you have an older cohort, and you're observing them in something that relates to that age, and there's a consequence of this age, will be affected by age, you obviously, you will see more likely, most likely will be an increased, okay, so, but you will see an outcome that is basically reflecting the older age of this cohort. So if it's hospitalization rate, older people are more likely to be hospitalized. If it's blood pressure, older people are more likely to have higher blood pressure or lower blood pressure if they have cardiac dysfunction. So this being said, this balance between both groups is really, really central to your interpretation. And regardless how you randomize them, so you randomize individual on an individual level between treatment arms. You can also block randomize them, so then you know that the confounders are essentially balanced within the blocks. And for that very reason, you essentially will have a balance between both groups on either level. And this essentially will allow you to look at results and outcomes and dynamics that are independent of confounding. And so given the extremely high costs of an RCT, the time it takes to recruit patients for an RCT and the ethical problems that come with RCTs, you can only imagine that you really want to have a good outcome for that money you have spent and the time you have spent. And one of them is here really that you have the highest level of evidence. You are independent of confounding because statistical methods help only as much with confounding. An RCT really, in a perfect world, eliminates confounding. Problem is it doesn't, but that's a whole different conversation piece. But yeah, to some extent it should. So it will minimize confounding to what is possible, to the extent possible. All right. So then RCTs. Okay. So RCTs are expensive, take a lot of time. Recruitment is an issue. They sometimes have ethical problems. In this context, I may talk about briefly about virtual trials. So right now there's an upcoming trend to essentially also conduct trials only. So you know how you have in vitro, in vivo, and in silico. So in vitro means like you do research in a rodent and in vitro, in a petri dish. In vivo means you study it in an individual or in an animal for that matter, but mainly in an individual already, what is mainly referred to. So you have a real life in vivo, VVO, live and pattern. You have an in life, real life study. And then you have lastly in silico. And in silico means everything just runs via computer simulations. And this is in times of high performance processing and high performance computing, and really up and coming technique that will get a lot of attention moving forward. So you basically, if you have a study that is expensive to do, takes a major time to conduct, and also or alternatively you run into ethical issues during the study because like nobody would ever conduct the study or no IRB would ever approve of the study, you can run this through in silico. You can run this through by basically using data and what is known in the literature to really simulate the outcome. Good. Okay. If we cannot do an RCD for whatever reason, we have to deal with observational studies. Yes, so observational studies, epidemiological studies is a really viable solution to a lack of information, a lack of available information. It is not perfect, not at all, but it is insightful. It generates hypotheses. It will clarify thinking. It will allow insights that have not been present here. It gives wonderful tools. It gives wonderful insights that essentially can be confirmed by replication. They can be confirmed by looking at it with different statistical methods, with different testing for interaction. So it's like there's a lot of things you can do with observation. So you can't really talk negatively about it. It actually gives a lot of input, and it's very useful to essentially know how to deal with all this data, and particularly in our days where so much data is accumulated on a daily basis. We have so much data, and we have so much work to do in figuring out how we actually can A, get a handle on this data, B, make sense out of this data, how to deal with it on an ethical and legal level, so there are so many open questions when it comes to data, that what is being done with observational studies and epidemiological studies, that knowledge that you are accumulating right now, this is such useful and important knowledge, and it really, it will inform the community moving forward. Okay, it's rambling off again. Okay, so we deal with observational studies. So I don't refer to doing observational research as have to deal with observational studies. I actually do very much enjoy observational research, and I think it's if at the very least it only generates hypotheses, it has fulfilled a great purpose. And our colleagues from clinical research are going to be very happy that they have some really good hypotheses at hand. So, so addressing confounding, regression is a commonly used tool, and it's a very important tool. And you will see why in the course of this class. So regression allows, so it's one of the tools that basically allows to deal with this. Good. Okay, so now I rambled off. Forgive me. Okay, so possible approaches to address confounding. So we talked about it. If everybody in my group, in my population, my study population, were of the same age, confounding wouldn't be an issue, right? Particularly when it comes to confounding by age wouldn't be an issue. So for that very reason, if you have a good sample size, you can just take people of the same age, study those. So you basically, you're creating subsets, and you look into subsets and you see whether the estimates differ. If the estimates differ, then you have a problem. If they don't differ, then you're fine. So maybe age isn't the problem. The downside is you need a really solid sample size to do that. Otherwise, you get an unstable estimate that doesn't really inform you much. The wide confidence interval is a low level of precision. And yeah, so that's definitely a major limitation. Another problem that you may run into, that by subsetting and stratifying your population, you're essentially introducing, or you're placing more weight on other confounders, which may be more present in older populations, right? Or in younger populations for that matter. So if you're interested in the association between glucose and blood pressure, it's like classic at this point, and I've mentioned it a million times, it's like a cardiac function, right? Cardiac function in younger people is known to be better than in older people. And now you're looking into 50 to 60 years old, 40 to 50, you're more likely to have an increased blood pressure because of stiffening of the vessels, because, I don't know, various reasons. Most common reasons are high levels of inflammation, smoking, lipids, reason that classically associated with arterial stiffening and elevated blood pressures. But now you look at an older age group, even that you go for the 60 to 70 years old, and there you have a whole different confounder coming in. You have congestive heart failure coming in. You have cardiovascular disease coming in. You have those that already had one heart attack at one point. Their blood pressure goes down. It's not a good thing, but it goes down. So it's you basically have a whole different confounder comes in that is really age specific, that may not have had that much weight if you would have looked at the overall population. So this is to be kept in mind. All right. Approach number 2 is multivariate regression. So this is where basically you are adding a second parameter into your model. So you are now at yi, your individual y, your individual blood pressure, plus the intercept, which is again where x equals 0. So this is again a blood pressure estimate, plus the beta 1 multiplied by x1. So this is still our blood glucose, plus the beta 2 multiplied by x2i, which is now an age estimate, and plus your error. And the error unchanged still is normally distributed around the mean of 0 with a variance sigma squared. And in that example, SPB is A plus B1 multiplied by SL. So this is the more pragmatic kind of depiction of this association of this model. And in R, it will present as it presents here. And this is also what we will be doing in the lab. So now, if you compare now adjusted and unadjusted regression, what you will see is that our initial unadjusted estimate is now being changed for a new intercept, which means that age did play a role in the intercept, which also makes sense because we're looking at a parallel shift by age, right? This is now shifting because it adds. And you have a higher slope. So with blood glucose, you will have actually a higher increase while holding the age constant. And this is important to keep in mind. So it's an estimate with a constant age at this point. All right. So the way this would present at in an R model is in the same fashion as with the univariate R model, and this is what we discussed last time, right? So we have up here, we have the formula. I outlined this in the lab. So this is the formula. This is the median. So we remember the mean is 0, but the median is here again, somewhat shifted to the left, to the negative. And we have here the third quartile, and we have a max that is kind of consistent with the min. So which means that there's more data shifted towards the positive. So we have an intercept of 115. We've seen that 1.93, and we have 0.443 H coefficient. So again, we have the residual standard error. So this is 4.9 on 97 degrees of freedom. So we have, again, now we remember, so we have now groups. So we have sample size -1 for each group. So we have 100 minus 3 because it's 3 groups now, right? It's blood pressure, glucose, and age. So now it's 97 degrees of freedom. So the residual standard error is 4.9. R square has dropped. If you remember, it was 0.75 in the beginning. The adjusted R square, not too strongly affected by this additional parameter, but we still have a significant model. And again, here we have the F statistic. So now if we are correlating the SPB with the fitted. Yeah, this is one way to do it too. So this is how you quantify the R squared. So you correlate your actual blood pressure with the fitted estimates, and this gives you. So this is the error of the estimate divided by the error of the actual values. So now this is the actual R squared, whereas the adjusted R squared is here 1 minus R squared multiplied by n minus 1. So you penalize for the number of groups. So here we have the actual sample size, and here we have the number of observations. So if we want to do this actually now in vivo, oh, no, we can't. Now let me see the data for now. Oh no, we can. Yeah. Okay, so if we do 1 minus bracket 1 minus 0.44888816 multiplied by n minus 1, which is 100 minus 1, divided by 100 minus 3 minus 1 gets us to 0.015. Okay, isn't that correct? Okay, so these are the things you always should try first before you actually do this class. Let me find what that issue is. Let's see what that is. Yeah, because it's not the R squared. Yeah, let me review this formula before we move forward here. That's not too easy in my head. Just a second here. Yeah. Okay. So here's another formula. So if we say this is R squared, hold on, 1 minus R squared, which is 0. Oh. Okay. It was totally my mistake. Yes, here we go. Okay, I had 0.044. Okay, apologies for that. Sounds like that you always should try first before you actually do that in front of the class. Okay, so you essentially, yeah, so you can easily calculate it. So I've never calculated it that way, so I knew the other formula we actually have to have this standard, the sum of squares. Okay. All right, so 1 minus 0.44 actually gets you there. Okay, so 0.4317, which is still somewhat different than what I would be seeing here, but there may be some. Okay. Let me look at this later. Good. Could maybe actually be the 2. Yes, here we go. That's actually 2. It's not 3 groups, it's 2 groups. Okay, my bad. Because the number is the number of covariates. It's not, okay. So again, thought process didn't go well. So the following. We have a residual standard error of 4.9 on 97 degrees freedom. We have 100, the N is 100. We have 100 individuals with 3 groups, 3 variables that go into this model. However, we only have 2 covariates. So you're subtracting 100 minus 2, 100 minus 3. 100 minus 2 minus 1 gets you to 97. So you essentially, you're getting to 1 minus 0.4488, which is the R square multiplied by 100 minus 1. So that's N minus 1. So you're penalizing it, the numerator by 99 divided by 97. So you're penalizing it by 99 divided by 197. All right. Good. So this is this. Alternatively, what you also can do, okay, please post questions about this. This is just really something I would encourage you to play around a little bit. It's really, I see a lot of merit in always having things calculated by, not by hand, but it's like to go through each of these calculations by hand. And this is why I give all the estimations, and I've seen the exams. You will need to have a solid handle on the arithmetic. So, okay, so results. So the Stargazer library allows for a nice output. And so if we look at our data here, let's run this through. Let's run this through. So you have the codes for this fit 1, fit 2. And here we have Stargazer coming in. So this is the estimate. This is this. Okay, library Stargazer. So with Stargazer, you actually can get an overview from fit 1, fit 2, title results from universe, and so this is the caption, right? Then we have type is LaTeX, which essentially pushes it into LaTeX in the PDF format. Style is default. You can make it so CR and F. I'm not sure what those options mean. Hold on. So you can get a Stargazer explanation, and I encourage you to read it. So it's really it's a very elegant way to essentially show style is default. Okay, omit stats SER and F, SER and F. I don't even see an F here, to be honest. Did we see an F here? I don't think we did. Okay, let's see how that looks like. Okay. Okay. That did not go down well. This is not as planned. Okay. Yeah, I'm not very savvy in Stargazer. If you have actually noticed by now, because. Okay. There's a fit 1, fit 2. Fit 1. That's one. Fit 2. Stargazer. Stargazer. Fit 1. Fit 2. Okay, not not too much of a problem as of now. We will discuss this in the lab anyways. I'm gonna do my research on the lab. Okay, so we have now lab 3. We actually have, okay. We will be running the code and we'll run it to replicate the lecture. Then we set different seeds and see how the results change, especially for sugar levels. We choose different magnitudes from observed confound effects. We refit the model and observe the change impact of SL to SPP. Try other changes you might consider, include the magnitude of error for SL and or SPP. Finally, write a for loop to gather results from 1,000 seeds and quantify the percent bias of estimating coefficients of SL due to omitting confounders. So we will convene soon, and I'll be posting the lab video already. That was the lecture, and please post your questions to the discussion board. Let's continue the conversation on topics. All right.